In this section, we'll discuss the various types of images in Coname 1 and their impact on performance. Coname 1 has a few image types: loaded RGB, built-in RGB Coname 1, mutable encoded image, multi-image, font image, and more. There are a few others, but I won't go into every nuance. All image types are mostly seamless to use and will just work with DrawImage and various image-related APIs for the most part, with caveats on performance. Performance and memory-wise, I'll review each type and try to explain the trade-offs involved with the image type you use. The Coname 1 designer tries to conserve memory and be clever by using only encoded image. While these are great for low memory, you need to understand the complexities of image locking and be aware that you might pay a penalty if you don't. Here are the pros and cons and logic behind every image type. This covers the logic of how it's created. This is the basic image you get when loading an image from the jar or network using image.createImage string, or image createImage input stream, image.createImage byte array, int, etc. The image is stored in RAM based on device logic and should be reasonably efficient in terms of drawing speed. However, it usually takes up a lot of RAM. To calculate the amount of RAM taken by a loaded image, we use the following formula: image width times image height times 4 equals the size of RAM in bytes. So a 50 by 100 image will take up 50 times 100 times 4, and that's 20,000 bytes of RAM. The logic behind this is simple. Every pixel contains 3 color channels and an alpha component, hence 3 bytes for color and 1 for alpha. This isn't the case for all images, but it's very common, and we prefer calculating for the worst case scenario. Even with JPEGs that don't include an alpha channel, some OSs might require that additional byte. There are 2 types of RGB constructed images that are very different from one another, but since they are both technically RGB images, we are bundling them under the same subsection. Internal is a close cousin of the loaded image. This image is created using the method image.createImageIntArray int and receives the ARGB data to form the image. It's more efficient than the Coname 1 RGB image, but can't be modified after it's created, at least not on the pixel level. The goal of this image type is to provide an easy way to render static RGB data efficiently at platform native speeds. It's technically a loaded image internally. RGB image is effectively an ARGB array that can be drawn by Coname 1. On most platforms, this is quite inefficient, but for some pixel level manipulations, there is just no other way. An RGB image is constructed with an int array that includes width times height elements. You can then modify the colors and alpha channel directly within the array and draw the image to any source using standard image drawing APIs. This API is very inefficient in terms of rendering speed and memory overhead. Only use this technique if there is absolutely no other way. Encoded image is the workhorse of Coname 1. Images returned from resource files are encoded images, and many APIs expect it. Encoded image can be instantiated via the create method in the encoded image class. Pretty much any image can be converted into an encoded image via the create from image boolean method. Encoded image is effectively a loaded image that is hidden and extracted as needed to remove the memory overhead associated with loaded image. When creating an encoded image, only the PNG or JPEG is loaded into an array in RAM. Normally such images are very small relatively, so they can be kept in memory without much overhead. When image information is needed, pixels, the image is decoded into RAM and kept in a weak/soft reference. This allows the image to be cached for performance and allows the garbage collector to reclaim it when memory becomes scarce. When drawing an encoded image, it checks the weak reference cache, and if the image is cached, then it is shown. Otherwise, the image is loaded and cached. Since the fully decoded image can be big, width times height times 4, the ability to store just the encoded image can save a lot of RAM. So taking our example from before, 50 by 100 image will take up 20,000 bytes of RAM for a loaded image, but an encoded image can reduce that to 1 or 2 kilobytes of RAM. Notice that an encoded image might be more expensive than a loaded image, as it will take up both the encoded size and the loaded size. So the cost might be slightly bigger in some cases. Its main value is its ability to shrink when it isn't used. Encoded image is not final and can be derived to produce complex image fetching strategies. For instance, the URL image class can dynamically download its content from the web. Naturally, loading the image is more expensive, so we want the images that are on the current form to remain in cache, otherwise the GC will thrash a lot. That's where lock kicks in. When lock is active, we keep a hard reference to the actual native image, so it won't get GC'd. This significantly improves performance. Internally, this is invoked automatically for background images, icons, etc., which results in a huge performance boost. This makes sense since these images are currently showing and they will be in RAM anyway. However, if you use a complex renderer or custom drawing UI, you should lock your images where possible. To verify that locking might be a problem, you can launch the Performance Monitor tool, accessible from the simulator menu. If you get log messages that indicate that an unlocked image was drawn, you might have a problem. I will discuss the Performance Monitor tool later. Multi-images don't physically exist as a concept within Codename1 API, so there is no way to actually create them, and they are in no way distinguishable from encoded image. The only built-in support for multi-images is in the resource file loading logic, where multi-image is decoded and only the version that matches the current DPI is physically loaded. From that point on, user code can treat it like any other encoded image. Performance of multi-images should be identical to encoded image with one major caveat. They increase the size of the resource file. Since most apps keep the resource file in RAM, for usage later, this might impact RAM's hence performance negatively. A workaround might be to split some of the data into separate resource files that won't be cached. However, in recent years, we tried to reduce the usage of multi-images in favor of font icons and similar strategies. Mutable images are created via image.createImageIntInt or image.createImageIntIntInt. They accept the width/height of the image and potentially the ARGB background color. Once created, a developer can invoke getGraphics on a mutable image and draw to its surface. The image can then be drawn onto the screen like any other image. In terms of performance, mutable images are the most interesting and most problematic features. Historically, when we started Luit and Codename1, mutable images were fast. In fact, we used them to implement common optimization technique of the day called double buffering. In double buffering, a developer draws onto a background image, then draws that onto the screen, resulting in fast, flicker-free rendering. This is strongly discouraged for modern devices, specifically Android versions newer than 2.3 and iOS versions newer than 4. Since both of these platforms are effectively dead, you should no longer use mutable images for performance. We even have an API in Display to detect that. Display.getInstance are mutable images fast. This usually returns false on iOS and Android. On iOS, creating a mutable image is even slower and might cause noticeable rendering delay if we are creating a large image. To understand why, we need to understand how modern rendering works. Modern devices use hardware acceleration aggressively, which means every rendering operation is sent to the GPU, the graphics processing unit, for fast processing. The more you can throw on the GPU, the faster your processing will be. Images like this are rendered in software and not in by the graphics hardware. So the underlying native OS will spend expensive CPU time drawing graphics in memory, and then more time copying that memory from the CPU RAM to the GPU RAM to actually draw it. You would also take up memory, specifically width times height times 4 amount, and sometimes even more than that. Mutable images are problematic, but sometimes they are the only way to accomplish something. For instance, if you want to create and save a new image, the only way to do it is through mutable image. However, there is also a performance case to be made for mutable images. If you have code that includes a lot of rendering operations that repeat themselves, it might make sense to pay the penalty of a mutable image once and then draw that. It's something we do with some special effects, which would be expensive to render repeatedly. We can just generate a rubber stamp. Once the mutable image is rendered, its drawing performance is as fast as a loaded image. Even though it has noticeable RAM overhead, it might still be worthwhile for a lot of use cases if you are willing to make the trade-off. One important bit of information is that mutable images aren't thread safe. This is a bit problematic, but there is no way around it. Mutable image access must be done on the EDT. Some optimizers have tried to use a separate thread to render mutable images. This might work for most platforms, but it doesn't work for iOS, which relies on a global drawing state. So this is one performance optimization tip you shouldn't use. Font image allows using an icon font as if it was an image. You can specify the character, color, and size, then treat the font image as if it's a regular image. The huge benefits are that the font image can adapt to platform conventions in terms of color and easily scale to adapt to the DPI. It also comes bundled with material design icons representing common functionality. In terms of performance, fonts are smaller than PNGs and JPEGs. They are much smaller than multi-image, both in RAM and distribution size. Rendering performance is hard to measure and depends a lot on the OS. Performance difference shouldn't be noticeable in the rendering layer. As a result, if you can use font image, then you should use font image. The image type has almost no overhead in terms of RAM, which makes it ideal. Some optimizations in the label rendering pipeline might be lost when using font image. However, that is an edge case behavior, and you should only deal with that if profiling highlights this as a performance bottleneck. It's possible to convert a font image to image, which internally uses mutable image or encoded image. There is no measurable performance advantage for doing that. The main motivation for doing this is APIs that might rely on image data behaving in a specific way. FontImage doesn't implement some common APIs such as getRGB, and some low-level APIs might rely on native image drawing, which won't work with FontImage.